Hello, good evening everyone. So my name is Abhishek Chantakri and I am an assistant professor, and today we are going to talk about the two-dimension flows in aerodynamics. Okay, so in this lecture you are going to study the uniform flow, the source flow, the sink flow and your doublet flow. Let's start with your first flow, that is your uniform flow. So consider a uniform flow with velocity v infinitive in x direction. Okay, these are elemental flows. That means the flow is incompressible as well as it is irrotational, which basically means that del dot v is equal to 0 in case of incompressible, since your rho is constant. Okay, now in this we are going to talk about two important parameters, that is your velocity potential, which is a scalar quantity, and your stream function. Okay, so velocity potential is basically del phi is equal to v, that is the gradient of your velocity potential gives you your velocity. Okay, now we are, as I told you, we are going to talk in two dimensions. So we have the velocity in x direction is u and the velocity in y direction is v. So dou phi by dou x is equal to u, and what is the velocity in x direction? It's v infinitive. So dou phi by dou x is equal to u is equal to v infinitive. And do you see any velocity in y direction? No. So the velocity in y direction is 0. Okay, now integrating equation 1 and equation number 2 with respect to x and y respectively, will get dou phi is equal to v infinitive dou x. So if you integrate that, you're basically going to get v infinitive integration of dou x is x plus a function of y. Similarly, constant, yes, 0, constant plus a function of x. From these two you can easily write v infinitive x should be equal to your g of x and a constant should be equal to your f of y. That means v infinitive x plus constant. Okay, now phi is equal to v infinitive x plus constant, but I don't need to write the constant because the derivative of a constant is 0, so I don't have to write it. Now to calculate the stream function, right, so the stream function is, for example, if there is u and v are the velocities of function x and y, then the constant will have like different the constant will have different values for different streamline. Okay, so basically in this case dou phi by dou y is equal to dou psi by dou y is equal to u, and the velocity in x direction is v infinitive. Similarly, dou psi by dou x is equal to minus v, but we don't have anything here, so is equal to 0. Now again integrating these two equations, that is equation number 4 and 5, with respect to x and y, we are basically going to get psi is equal to v infinitive y plus constant. Again the constant, right, derivative of constant 0, so I can write it as v infinitive y. Next, let's look at this thing here. Okay, basically I'm going to talk in terms of polar coordinate, right? So my x by r is nothing but your cos theta and y by r is sin theta. That means x is equal to r cos theta and y is equal to r sin theta. So now what we have to do next is you just have to substitute the values of x and y for your phi and psi. Okay, so just substitute in those equations, you are basically going to get psi is equal to v infinitive r sin theta and phi is equal to v infinitive r cos theta. So after this we are going to look at circulation. Our basic definition of circulation tells me it is a line integral along a closed curved path. Okay, so line integral along a closed curved path. So let me take this as your closed curved path. Okay, and this, let me take it as L and this as H. Okay, so now basically you are taking that curve and I'm just going to substitute here. Okay, so that means my minus v infinitive L minus 0 of h plus v infinitive h plus 0 of h. So b infinitive h, v infinitive L gets cancelled. We are basically left with 0 here. Okay, again if you do then v infinitive ds is equal to minus v infinitive of ds, and ds again line integral of a ds around any closed curve is equal to 0. That means your circulation is basically equal to 0. Now if you want to write your circulation in the terms of your surface integral, then it becomes double integral of del cross v ds, negative of line, so negative, always negative will be there. Okay, so minus of double integral of surface del cross v ds. I know my del cross v is equal to 0, irrotational flow, that's why my circulation is equal to 0. So this is basically your first type of elemental flow, that is your uniform flow. Next we are going to talk about your source and sink. Okay, so basically what happens in this is, from all the points it comes to a single point, oh, then it is sink, and from one point the streamlines are directed in all possible directions from a single point, then it is your source. Okay, a single source, from there it is going in all directions, so we call it source, the streamlines, right? And all the streamlines are emerging at one point, then we call it sink. Okay, now you can see that this is like there is some constant radius, right? This is all, if you draw this it becomes a circle with a radius, that we're going to discuss how that comes and all. So basically you're going to have only your radial component of velocity. You have two components, right? One is your radial component, the other was your tangential component. So I don't see any tangential component of velocity in this case, which is equal to 0. So I only have my radial component of velocity. Okay, now we know that it is incompressible at all the points. Del dot v is equal to 0 at all the points except at the origin, because at the origin it is infinite. Okay, infinite. In sink flow it is again directed towards, as I already told you, and it is just a negative of your source flow. Okay, now let me just take, you can see a cylindrical coordinate that I have taken here. Okay, so let O be the origin, and origin can be of source or sink, anything. Okay, now only contribution is from my radial component, right? The velocity is only contributed by my radial component. So radial component is Vr. Vr is equal to constant by r. That means velocity is inversely proportional to my what? Radial distance. I am assuming my radial distance as r. Now I'm taking a cylinder of radius r as well as length L. You can see length L and radius r. So basically that is the cylinder that we have. Okay, now how you'll find the mass flow? See, mass, if I want to, I'll take a small element here. The element I have taken is ds. Okay, so mass flow across ds will be rho v ds. That is mass flow rate. What is the formula for mass flow rate? Mass flow rate is basically rho av, right? So area is ds, v is your this. Okay, now which velocity? So which velocity you have? Only radial component. So you're going to substitute here vr. Okay, so rho vr into ds. What is the area? Area is this into this, right? So this r d theta into L. Okay, now this was your elemental mass flow, or I say small mass flow. If you want to calculate your total mass flow rate, you just have to integrate, because see, if you are just, this is small d theta, right? We need ds, so we need the whole s. If you need the whole s, you need to integrate. So integrate over here, over the entire that. So that is basically 2 into 2 pi, right? 2 pi. So 0 to 2 pi, substitute this d theta, you're basically going to get 2 minus 2 pi minus 0. So you're going to get 2 pi rl rho vr. Okay, now what is your volume? Volume is mass by density. So volume flow rate will be v dot is equal to m dot by rho. So your equation, previous equation, you just have to remove your what? Yes, you just have to remove your rho from it. So basically it is 2 pi rl vr. Now this we found our volume flow rate. Next, the rate of volume flow per unit length of the cylinder is given by per unit length of the cylinder, that is divided by L. So V dot by L. So that is 2 pi r VR. Correct. Because that L will be gone now. So what will be left with? We'll be left with 2 pi r VR. So VR is equal to lambda by 2 pi r VR. Okay. And what is your lambda? This lambda is basically, lambda is known as your source strength. Okay. It is positive in case of your source and negative in case of your sink. Now again we are going to find your velocity potential and your stream function. So velocity potential, right? So it is for that is your two components of velocity. I told you your v theta is equal to 0. So VR is nothing but dou phi by dou r, yes, is equal to, if you do a dou phi of dou r of this, you're basically going to get lambda by 2 pi r. This 1 by r dou phi by d theta, v theta is equal to 0. You don't have to worry about that because it's 0, right? Now if you integrate this, if you integrate, yes, what you're going to get? You're basically going to get ln r, right? So ln r plus constant. We have done it previously. Similar way, we can directly write phi is equal to lambda by 2 pi ln r. Okay. So basically you are first going to get lambda by 2 pi ln r plus function of this and this constant plus function of this. You don't have to do all that. Just you can write phi is equal to lambda by 2 pi ln r. Now the stream function will be given by 1 by r, yes, 1 by r dou psi by dou theta, which is equal to VR. So VR is again lambda by 2 pi r, 2 pi r, correct? Yes, lambda by 2 pi r, and minus dou phi by this is equal to 0. Don't worry about it. Again, you're basically going to get integration of this equation is basically going to give you lambda by 2 pi theta. So that is your stream function. So found your stream function as well as your psi as well as phi, right? So your stream function as well, velocity potential. Now see, so how can you find the equation of a streamline? Now you can calculate it by substituting this is equal to constant. So if lambda by 2 pi theta is equal to constant, that means theta is equal to constant. Okay. And theta equal to constant is a straight line in polar coordinates. In polar coordinates, if theta is equal to constant, is a straight line. Okay. Similarly, you have your r is equal to constant. R is equal to constant is a radius of a circle with center at origin. So that's why here I have drawn, right? Yes, you can see this. That's why this circle was drawn. Yes. So that's basically it. Now circulation again our same formula, surface integral del cross V ds. Okay. So we again I know del cross V is equal to 0. So your circulation is equal to 0. These equations, that is these two equations what we have found, right? Equation number 4, that is phi is equal to lambda by 2 pi ln r, and equation number 7, that is lambda by 2 pi theta, satisfy our Laplace equation if you just substitute del square phi and del square psi is equal to 0. Therefore, since it satisfies and it can be written in terms of cylindrical coordinates, we are using this for complex flows. Now we are going to talk about the next very interesting topic, that is a flow characteristic or doublet. We call it doublet flow. So it is basically a combination of your source and sink, right? It leads to some singularity, that is doublet. Okay. In this case, what you have to do is consider a source of strength lambda, okay, and you have to consider a sink of minus lambda. Okay. So basically you have, if source is plus lambda, this is minus lambda, and they are separated by L. L is the distance between them. Okay. So stream function will be given by, see there are two things, right? So stream function will be given by, one second, yes, psi of 1 plus psi of 2, correct. So basically psi of 1 is lambda by 2 pi theta 1 plus lambda by 2 pi theta 2, but sink is minus lambda, so that's why it becomes lambda of theta 1 minus theta 2 divided by 2 pi, or I can write it as delta theta as you see in this PPT here. Okay, so now this, what is doublet? So you have to assume that this shrinks, that means this tends to 0 and the magnitude of L into that, yes, L lambda is constant, that is the magnitude of L lambda is constant, maintaining that L tends to 0. When you reach that spatial flow pattern, it is known as your doublet. Okay, now the multiplication of lambda L is equal to kappa, and this is known as your strength of your doublet flow. Okay, now the stream function for a doublet flow, what did I told you? I told you, right, limit tends to 0. So basically limit x tends to 0, yes, minus lambda by 2 pi d theta, and what is important here, lambda L is equal to constant. So when that condition is met, my doublet flow condition is satisfied. Okay, so in this, what is happening, the limit is tending to 0, right? So what happens, since it's tending to 0, the source will achieve some infinite value. Okay, now look at this figure here, consider R and B, yes, B the distances from the source. Okay, R and B is the distance, you see R and B is the distance from the source and sink respectively. So this is your source, this is your sink. So R and B is the distance from your source and sink respectively. For, let's say, for small d theta, okay, small d theta, if you see this, A by L is equal to basically sine theta, that is A is equal to L sine theta. Similarly B is equal to, this is A, okay, this thing here is A. Okay, so A is equal to L sine theta and B is equal to R minus this distance, right, R minus L cos theta. So d theta is basically A by B, so that is your L sine theta by R minus L cos theta. Now what you have to do is substitute the value of d theta in that equation we had before, right? So basically minus lambda by 2 pi L sine theta by R minus L cos theta. So it was minus lambda by 2 pi d theta, right? So basically d theta is nothing but del theta, just substitute the value, you are going to get this. Okay, next, what is your lambda L? Lambda L is kappa, so minus kappa by 2 pi sine theta R minus L cos theta. I hope this is clear up to here. Next, my limit is tending to 0, right? Basically my limit tending to 0, it's not x, it is actually L here. Okay, this is L. Okay, so limit of L tends to 0. So if L is tending to 0, that means this part is gone. What I am left with, I am basically left with sine theta by R minus k by 2 pi sine theta by R. Okay, so minus k by 2 pi sine theta by R. This is my stream function. Similarly, my velocity potential, I don't have to solve, I can directly write k by 2 pi cos theta by R. Okay, so I have got my stream function as well as my velocity potential. Okay, so minus k by 2 pi sine theta by R is equal to constant, right? So that is, if I write it as C, what is my R? R is basically minus k by 2 pi C sine theta. Yes, is it correct? So this is nothing but a equation. What is this? R minus d sine theta. This is nothing but R minus d sine theta. This is the equation of a streamline in doublet flow, equation of a circle, yeah, equation of a circle, and this is the diameter. So basically, what is my diameter? My diameter is k by 2 pi c. If I look at those two equations, R is equal to d sine theta, right, and R is equal to minus k by 2 pi c sine theta. So basically, what is my diameter? My diameter is k by 2 pi c. This diameter is a doublet family of circles that you see on your screen here. These are your family of circle, and all these different circles, they corresponds to different values of constant. Okay, since we have placed the source left to the sink and right, and the sink right to this, so basically what is happening, that the direction of the flow is out of the origin to the left, and similar, okay, out of the origin to the left. Again, my limit is tending to 0, This means that the source and sink will fall on top of each other, but they will not be equal to 0 because they are of absolute magnitude and their strength is going to become infinitely large. That means they will be infinite, or it will be an indefinite form, and this will have a finite value. Okay, so basically it will not be equal to 0. At that point del dot P is nothing but infinite, as I told you in the beginning. I hope this lecture is clear. If you have any doubts, you can ask in the comment section. Thank you very much. Have a good day. Bye bye.